Hello all of you. Welcome to the 41st lecture on the course on analysis and modeling in chemical engineering. In the last week, we started talking about graph theory. We discussed various notions of the graph theory such as the Boolean matrix R that basically tells me the connectivity between different vertices. We also discussed the idea of incidence matrix M that basically tells me like the information regarding the edges that connect the different vertices. And then we also discussed this augmented incidence matrix A that is pretty much similar to M, but it also contains columns that contains information regarding the interfaces. Keep in mind that the Boolean matrix does not contain information regarding interfaces. It only contains information regarding the internal connections between the vertices. The incidence matrix as well does not contain information regarding the interfaces, but augmented incidence matrix does contain that information, and therefore I can basically use that matrix to basically construct the balance equation where B is equal to a null vector O and Y is the column vector containing the edges which may correspond to, let us say, flow rates, right. And then we discussed how we can basically decompose or decide the priority order of solving the material balance or other flow equations on a flow sheet, right. And the idea basically began with starting from the Boolean matrix R to look for columns containing all zeros, then rows containing all zeros, then identifying the cyclical nets that has to be done simultaneously and things of that sort, right. So, we will take some examples of that approach further. And what we have also discussed is how do we identify the cyclical nets. We have discussed the notion of reachability matrix R star, and then we said that if I do R star intersection R star transpose, that gives me information regarding cyclical nets. We have discussed the idea of maximal cyclical nets, which are cyclical nets which are not sharing any common node, or they are basically every other cyclical net is a subset of that cyclical net, and we will take some examples on that, right. So, let us now take some examples of graph theory before moving to basically another application of graph theory in solving nonlinear system of equations. And then in this week, we will also discuss how the graph theory is used in other contexts, such as in analyzing the reaction mechanisms and so on. So, let us take some examples before we go further. So, in this problem, we are given the input and output edges for a process flow sheet, and we are being asked that which of these edges correspond to the input and output interface. How do you figure it out, right? So, there are 7 units in the flow sheet, and we are specified the listing of the edges. They go from A to N, and the listing of edges categorized by input and output. So, let us first figure out how can we identify the interfaces. Interfaces are going to be the edges that is only present as either the input or output for only one of the unit. If the edge is an output of one unit and input of another, this is the edge connecting two vertices in the graph. That cannot be an interface. For that to be an input interface, it must be input to a single unit and output from nowhere. For this to be an output interface, it must be output from one unit and should not be input to any other unit, right. So, let us see this in practice. So, let us say for example, if I look at the edge A, so we locate whether A is the output edge of any of the other unit, and we see that it does not, right. So, therefore, A is an interface, and this is clearly an input interface because it is input to unit 2. This is for unit 2. And then similarly, we go ahead and do for B. So B is an input is here, and we try to locate B as an output. We see that B is an output from 7. So B cannot be an interface. Let us see C similarly. So C is an input here and an output here. So C cannot be an interface. Let us look at D. So D is an input here, but D does not feature in the output edges. So D therefore must also be an input interface at vertex or unit 4. Similarly, for E, we try to locate E here. E is not present in the input edges, but E is present in the output edges. So E actually is an output interface for the again the vertex 4. F is present both as input and output. G is present both as input and output. H is present both as input and output. I is present both as input and output. J features in the input, but J does not come in the output. So J is again an input interface at vertex 3. Then K is present in both of them, both input and output. L is not present in the input, but L is present only in the output here. So L therefore becomes the output interface for unit 1. M is present in both, and N is again not present in the input, it is present as an output here. So N becomes the output interface. Right? So you can see how simply we can identify the input and output interfaces in the flow sheet. The next part of the question asks you to draw basically a Boolean matrix, right, for this graph. First of all, we have to do the graph and then do the Boolean matrix for this case, right. So, the first step what we will do, whatever edges that we have identified here, these edges are interface edges, they do not anyway are considered for the Boolean matrix, because that considers only the edges that connect different vertices. So, we delete A, D, J and E, L, N from here, and for the remaining edges I want to basically draw the connection. So, we start from B. B starts from 1 and goes to 7. So, we draw an edge starting from 1 going to 7. This graph will become quite messy because we have many edges. So, be careful how we are doing it. C is input to, by the way, B is coming from 7 to 1, sorry, other way around. C is coming as an input to 1 from 4, and D was an interface, we do not consider that. E was an interface, we do not consider that. F is output from 4 and input to 6. G is output from 2 and input to 5. H is output from 2 and input to 7. I is input to 6 and output from 3. And J is an interface. K is coming from 7 to 5. L is an interface. M is coming from 5 to 7. And N is again an interface. right. So, you can basically draw the graph by labeling all the edges. We can quickly check it. So, for 1, the input edges are B and C, which is coming here. For 2, there is no input edge, there is output edges G and H going to 5 and 7 respectively. For 3, there is an output as I going to 6. For 4, there is an output as F going to 6 and output as C going to 1. For 5, there is an input as G coming from 2 and there is a input as K coming from 7 and there is an output as M going to 7. For 6, there is a input as I coming from 3 and input is F coming from 4, and for 7 we have input edges M and H coming from 5 and 2 respectively, and output is B and K going to 1 and 5 respectively, right. So, we can see that we have drawn the quite messy flow sheet, right. Let us try to do the Boolean matrix for this case. So, we do label something like this: 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, and from 1 we have to see where are we going to. So, from we can see here from 1 there is no output S. So, from 1 we are not going anywhere. From 2 there are output S's G and H going to 5 and 7 respectively. So, from 2 I am going to 5 and 7. From 3 there is no input, but I am going to 6. From 4 I am having an S, F and C, which is going to 6 and 1. And from 5 I have a input as G and K. So, G comes from 2, that is already there, and K will come from 7, that we care about when we do the column corresponding to 5, right. So, let us only look at the output edges. So, from 5 there is an output as M going to 7, and from 6 there is no output as. From 7 there is an output as to 1 and there is output as to 5. So, I have 1 and 5 coming there. So, now we want to do the priority order of solving these equations using graph theory concept, right. So, we go back to our idea, we look for the columns in this matrix containing all R's, and in this case what are the columns containing all zeros? This is corresponding to 2, 3 and 4. All these columns contains all zeros, right. So, my first step is going to be basically solve 2, then solve 3 and then solve 4 pretty much in any order. And now, I am going to basically delete this 2, 3, 4 from the graph, that corresponds to deleting the rows and columns corresponding to 2, 3 and 4, and now I have the remaining matrix 1, 5, 6, 7, where the first row is all zeros, the row for 5 is having a 1, the row for 6 is now all zeros, and row for 7 is having 1 and 5. Now we again look for the columns containing all zeros in the new matrix, and we find that 6 is containing all zeros. So, we delete the row and column corresponding to 6 here, and we update here solve 6 after 2, 3, 4, and then I am left with 1, 5 and 7, and my reduced matrix is going to look like from 1 I am not going anywhere, from 5 I am going to 7, and from 7 I am going to 1 and 5. And now we can see there are no columns containing all zeros, but there is a row containing all 0 that is corresponding to vertex 1. So, this I can keep it for last. So, last step I will solve 1, and now I am left with 5 and 7. So, we delete the row and column correspond to 1. So, this is my reduced matrix, and now you see that there is no columns remaining. So, 5 and 7, it is looking like this. So, now there are no columns containing all zeros, and now no rows containing all zeros. So, the next step what we do, we compute the R square, and R square in this case will give me something like this, because there is indeed a cyclical net between 5 and 7. From 5 there is an edge going to 7, and from 7 there is an edge going to 5. So, there is a cyclical net here, and you can see sometimes the numbering is not so intuitive. Although there is a cyclical net, it is difficult to identify from this graph unless you do the Boolean matrix, right. So, we have a cyclical net of order 2 as the diagonals are 1, and clearly now there are no ancestors or descendants left in the graph. So, we will solve 5 and 7 simultaneously, right, and we already have figured out the last step, that is solving 1, right. So, we basically have a solution scheme for this graph using the graph theory concepts. Whatever we have done, this becomes the priority order. So, let me list it. So, we have figured out that we have to solve 2, 3 and 4, and we can do it in any order, and after that we can solve 6, and after that solve 5 and 7 simultaneously. That is the only order 2 cyclical net present there, and finally solve 1. So, we have got this priority order for this equation. So, now the question asks that if the edges correspond to the mass flow rates and the system is operating under steady state conditions, then what is the degree of freedom for this particular flow sheet, right. So, we can see that we have 7 equations because we have 7 units, and we can say here we have variables going from A to N. So, we have 14 variables. So, in total the degree of freedom is 7 in this particular case. So, we look at another problem where what is given is the augmented incidence matrix. In the earlier case we had the tables containing that edges given, and now from the augmented incidence matrix we need to figure out in the first part of the problem what are the system interfaces, right. What we can also see here is that it is not following the typical convention that I have defined, that the interfaces are to the end of that last columns, right, because there are some columns here containing only one entry that corresponds to an interface, but it is somewhere in between, as we will see, right. So, let me just label the vertices 1 to 10, and the edges. So, we have 16 edges, And what we see here, as I was just mentioned, that E1, for example, this column contains only one. That means that E1 corresponds to an interface, but unlike the typical convention which I have given, it is not towards the end of the last columns, right? Because the initial part was supposed to be the incidence matrix and interfaces should come in the last columns. That is not the case here. So, for whatever reason, so we have to take care of that. So, E1 is an interface which is incoming at 1. So, it is an input interface. Then E2 has two entries, -1 and 1. It is outgoing at 1 and incoming at 2. So, it is not an interface, it is internal node. Internal is E3 also in internal, E4 is internal, E5 is internal. Wherever we have two entries -1 and 1, they are internal edges. And then E9 is having only -1 here, which is outgoing from 10. So, this is an output interface from 10. Then we go further, and E11 is also an output interface from 9, and all the other edges correspond to internal nodes. So, we have three basically interfaces identified. Now, let us also look at the degree of freedom for this system. So, we have 16 edges corresponding to 16 variables, and we have 10 vertices corresponding to 10 equations. If it is a steady state, then we have 10 steady state balance equations. So, my degree of freedom is 6. If we, for example, choose these three interface variables as given as per the common practice, we still have the liberty to choose three other variables as given, right. And what we will do in this example is we will choose the variables that will kind of give you a maximal reduction in the graph, right. We will do it by inspection, but it can be also be formalized as we discuss later, right, by the idea of tiering and all that, right. So, but in this particular case, we will try to reduce the graph purely by inspection, right. So, let us first try to do the graph for this case and the Boolean matrix for this case, and then we can see which one gives me the highest reduction, right, at least visually, right. So, let us try to do it quickly. So, we go column by column and we draw the edges in my graph. So, E1 is already identified to be an interface. So, we do not worry about it. It will not feature in the graph and in the Boolean matrix, right. E2 is coming from 1 going to 2. So, this is my E2. E3 is coming from 2 going to 3. E4 is coming from 3 going to 4. Then E5 is going from 4 to 5. Then E6 is going from 5 to 6. Then E7 is going from 6 to 5. Then E8 is going from 6 to 10. And E9 is again an interface, so don't worry about it. E10 is going from 6 to 9. And E11 is an interface. E12 is going from 3 to 7. E13 is going from 8 to 7. E14 is going from 7 to 8. E15 is going from 8 to 2. And E16 is going from 2 to 4. Now the question is, which other three variables I will take it as given, right? The choice is very clear. Wherever we have a cyclical net, we need to solve the equations simultaneously, right? So let us first figure out where are the obvious cyclical nets we see in the graph, and at least one of the edges for each cyclical net we should take it as given, right? So what I do here is I choose E7 as given, and once we do that, once we choose E7 as given, I can delete this particular edge from the graph. Similarly, we can take E13 as given, that is right here, I am taking it as given. So we can get rid of E13 from the graph. And finally, now we do not obviously see a cyclical net in the graph by inspection. So let us try to choose any of that may make things easier. So I am going to delete E15 from there, that is from 8 to 2. At least visually it appears to create a problem. So let us get rid of also E15. So now we have three interface variables given and three other variables I have chosen to be given. Then I am left with only 10 variables in 10 equations. Let me get rid of this. And now we are going to do a Boolean matrix for this particular graph, the simplified graph. So in the Boolean matrix, I will have the vertices along both rows and columns. Now from 1 I can go to 2 in one step, that is the only place I can go to. So I put a 1 there. From 2 I can go to 3 and also 4. From 3 I can go to 4 and 7. Then from 4 I can go to 5. And from 5 I can go to 6. And from 6 I can go to 8 and 10. And from 7 I can go to 8. And from 8 I cannot go anywhere. And from 9 I cannot go anywhere, and from 10 as well I cannot go anywhere, right? So now you see, given that we make these choices, you have a matrix that is quite easier to work with, right? If you look along the columns of the matrix, that is to locate the vertices with no ancestors, we have 1 and 9 having 1 and 9 having no ancestors in the graph, right? So 1 and 9 is having no ancestors. So in fact, we can get rid of 6 2 By the way, from 6 I can still go to 9. I cannot go to 8, sorry, let me correct it. From 6 I can go to 9 and 10, right? So yeah, please note that correction, right? From 8, however, I cannot go anywhere. Right? So now you see that if I look at along the columns, the vertex 1 is without any ancestors. So it makes a very clear case that we should solve the balance for 1 first. Now, once we solve the balance for 1 first, once we have figured that out, then we can basically get rid of the first row and the first column. And now in the reduced matrix, you can see the ancestors of 2 are not present. So I can now solve the balance for 2. And now we can get rid of the rows and columns corresponding to 2. And now you see that now the 3 has no ancestor. So now we can solve the balance for 3 and delete the corresponding rows and columns. And once we do that, then we can see that 4 is having no ancestors. So we can get rid of the rows and columns corresponding to 4. And once we do that, we see that 5 is having no columns. Keep in mind that this is happening because we have chosen the variables as given appropriately, right? For other choice of variables, it may not have been that straightforward, right? So for 5 will come next. So now we can get rid of this. And then we can see that now we can get rid of 6 and 7 in any order. So we can get rid of 6 and 7 in any order. And now pretty much we have the vertices remaining that has no ancestors, no descendants. So we can now solve 8, 9, 10 again in any order. So provided that we choose the guess variables properly and graph theory can help with that, we can have kind of an straightforward way of solving this kind of equation, right? That's another use of the graph theory, right? Now the question also asks you to write the flow equations, the balance equations for this case. The augmented matrix is already given. So the balance equation for the steady state case is given as A dot y equal to 0, where y is my column vector containing all the edges including interfaces E1 to E16. I will not write all the balance equations, but we have done that before, right? And finally, we have already figured out the priority order for solving the equations as we have seen in this, right? So by proper choice of variables, we can basically reduce the graph to something that is not having cyclical nets at all. So we can pretty much, for every cyclical net, we can choose one of the variables as input so that the cyclical net is kind of broken, and then my decomposition becomes quite straightforward. So with that, I conclude the discussion in this lecture. In the next lecture, we will look at how can we decompose a nonlinear system of equations also using graph theory. So with that, I stop here. Thank you so much.